Today we're doing optimization problems, which means that we're looking for when a situation is the maximum or minimizing. So we're maximizing or minimizing like profit or area or any kind, whatever we're measuring, volume. Okay. So we're basically going to apply the first derivative test here. So what we want to do is we always want to make sure we label our figures. We write the primary equation, which has what we want to maximize or minimize. So if we want to minimize the volume, we want to write a volume equation. Then we probably need to switch out some of the variables. So in order to do that, we write a secondary equation where we can make some substitutions. We always want to think about what the domain of our situation is. And then finally, we take the first derivative, make our number line, and test for relative minimums or maximums. All right. So first up, manufacturer wants to design an open box having a square base and surface area of 108 inches. So I can see a square base and a surface area of 108 inches. What dimensions will produce the box with the maximum volume? So we want to maximize volume. So our primary equation is going to have something to do with volume. What we want max volume. When the surface area is equal to 108 square inches. Okay, so other things we know is that the base of the box is x and x because it's a square, and then the height, we don't know what the height is at this point. So we know we need the two dimensions of the base to be the same, and then the height can be something else. I know that the volume, okay, the volume is base times width times height. So it's x times x times x times height, which is x squared times height. All right. Okay, so next up, let's see. So our primary equation is x squared times height. And I probably, since I know that I have information about surface area, I also probably need to make an equation that includes surface area so that I can replace some of these variables with some number information in them. Okay, so I see my face is in the way. Okay, so we're going to do surface area. So this is our secondary equation, is surface area. So the surface area of the box would be x times x is the base. Each one of the sides is x times h, so plus xh. And then there are 4 of those sides. 1, 2, I should not put x's. Okay, there's 1, 2, 3, 4 sides times 4. We do not include the top because it says it's an open box. So I have the surface area is equal to x squared plus 4xh. And then I remember that surface area was equal to 108. So that is x squared plus 4xh. And I realized that if I solve for h, I can replace h later with, so if I solve for h, I have an equation that's written in terms of x, and I can replace that later into our v equation. So I have h, let's see, 108 minus x squared divided by 4x is equal to h. Yep. Okay. So now we go back to our main equation. The volume is equal to x squared h. and I replace h with 108 minus x squared. The fewer variables, the better, the easier it is for us to evaluate. Okay, so I'll simplify, giving me, let's see, my x's cancel. So I get x times 108 minus x squared over 4, or all over 4, doesn't matter. I'll divide 4, I'm going to go 108x minus x cubed all over 4, and I'll go ahead and divide that in, giving me 27x minus 1/4 x cubed. And really, that's a lot better because it's pretty easy to take the derivative of that. So I'll go ahead and do that. Oops, I put x here. Let's go ahead and fix that. That's volume. Okay. So now we're going to go ahead and take the derivative. So dv over dx with respect to x this time. Okay. So as the dimensions of the base change, how does the volume change? Okay. I get 27 minus 3/4 x squared. And then we find our critical numbers, which is, looks like nothing is undefined. So 0 is equal to 27 minus 3/4 x squared. I get negative 27 is equal to, actually, let's do positive. So 3/4 x squared is equal to 27. X squared multiplied by the reciprocal. I get 36 square root. I have x is equal to plus or minus 6. We cannot have the negative 6 since the dimensions of the box need to be greater than 0. See, our domain. So the dimensions of the box would be, oh, this is very challenging. Okay, so x, the base is 6, the other base is 6, and the height we will solve for, which we have right over here. The height is equal to 108 minus x squared all over 4x. And so we can say the height is equal to 108 minus 36 over 36, 24. Wow, 24. Okay, which gives us a 3. So the dimensions are 6 by 6 by 3 inches. Okay, and that's problem number 1. Let's move on to number 2. Let's maximize the area of this paper. All right, so we got some paper. It's a rectangle. The writing area contains 24 square inches of print, and then the margins at the top and bottom of each of the pages is 1.5 inches. And then the margins on the left and the right are 1 inch. So I kind of started drawing this out. On the inside, the area is 24 inches squared. Okay. And then on the margins, it says that the tops, so right here, is 1.5 inches. And then the margin on the bottom is also 1.5 inches. And then the margins on the side are 1 inch. It's a 1 inch. Okay, so what we want to do is, what should the dimensions of the paper be so that the least amount of paper is used? So this overall area, we're going to minimize the overall area of the paper. Oh, no duh, I put it right here. Okay, minimize the area. So the area of the paper overall is equal to base times height, right? So the width, or the base, would be, I'm just going to go ahead and label this x, and y for the green, x and y. So then the base of the overall paper would be x plus 2. This is the base times the height. Okay, so x plus our 2 inches, and then our y plus our 3 inches. Okay? All right. Up next, we need a secondary equation because we need to start plugging in some values into our situation here. So our secondary equation is the surface area of the inside, so the green part right here. I know that the inside piece is 24 inches and that the area equation would just be x times y. That's lovely. All right, I am going to solve for x. It really doesn't matter. You can choose either, especially since we're going to have to find all the dimensions for x and y anyway. So I solved for x on my paper, so I'm going to just do that. So x is equal to 24 over y. Now I can use that secondary equation in my primary. So the area is equal to 24 over y plus 2 times y plus 3. Now we multiply. So I'm going to go like this. So that's 24 plus 72 over y plus 2y plus 6. All right. Simplify. Area is equal to, I have 30. Those combine 6 and 24. Plus 72 over y plus 2y. And then, I'm all about the power rule if I can use it. So I'm going to do y to the negative 1 plus 2y. And I am just going to remind myself that the domain is that x has to be greater than or equal to 0, and same with y. Okay. Next up, we take the derivative. Since I have my primary equation here, I'm going to take the derivative to use the first derivative rule. So we're taking the rate of the area with respect to y. So I get, let's see, 30, derivative of 30 is 0. Then I get negative 72y to the second power plus 2. All right, so dA dy is equal to negative 72 over y squared plus 2. I can see right now that I have a critical number at 0. Yeah, okay. So a critical number at y is equal to 0, since that's what makes the graph undefined here. And then let's solve for our zeros. So I have 0 is equal to negative 72 over y squared plus 2. And so 2 is equal to 72 over y squared. I'm going to multiply both sides. I'm just going to cross multiply. So I get 2y squared is equal to 72, or y squared is equal to 36. So y is equal to plus or minus 6. Okay? I see right now that y is equal to 6 and y is equal to negative 6. Y cannot equal negative 6. So what I need to do next is do my, all right, we got to make a number line, which I forgot to do on the last example. So f prime, our domain is that we have to be greater than 0, and our critical number is at 6. So I tested f prime of 2, and I got a negative value, and I tested f prime of 7, and I got a positive value. So I can see that at y equals 6, we have a relative minimum. So we are minimizing the area at y equals 6. Okay. So all that's left is I have to get the dimensions of my paper. Okay, so I have area of the inside is equal to x times y. So 24 is equal to x, and the y is equal to 6, so x would equal 4. So I'm going to take, now I just need the dimensions, the actual dimensions, so adding the margins. So I have x plus 2 is equal to 6, since x is equal to 4, and y plus 3 is equal to 6 plus 3, which is 9. So the dimensions of the paper are 6 by 9 inches. Okay, let's go back to the first one, and we'll just do a quick number line check to make sure that we actually maximize the volume. So I'm going to set up a number line. The domain has to be greater than 0. Okay, and I have a critical number at x equals 6 again. So this is v prime. And when I plug in something like v prime of 1, I get a positive out. And if I plug in v prime of 7, I get out a negative. So we are increasing, then decreasing. So these dimensions will maximize the area, not maximize the volume, not the not minimize. All right, 2 more examples. So again, we're going to minimize the area. So this time a farmer has 100 yards of fencing to form 2 identical rectangular pens and a third pen that is twice as long as the other 2. So I drew you a picture here. Okay, so the 2 identical pens and then one that is twice as long. All 3 pens have the same width, which is x, and which value of y produces the maximum total fenced area. Okay, so it looks like we have, what we want to do is maximize area. So our primary equation needs to be about area. So the area of the pens is basically the outsides. So this outside piece would be, if I cut it right here, that would be y, y, x, x. This is y, y, and x. So I just labeled every piece. Why not? All right, so the area would be 2x. So the length of the side is 2x times 2y. All right, so area is equal to 4xy. And then we need to swap out one of the variables and use this 100-yard parameter. So my secondary equation would be about, since it's 100 yards, it's going to be about perimeter. So the secondary needs to describe the perimeter. So the perimeter is all the fencing here. So every place I'm going to place a fence. So that would be y. So 6y. Yeah, 6y plus 1, 2, 3, 4, 5 x's plus 5 x's. And we want a perimeter. We have a total of 100 yards to use. So the perimeter has to equal 100. And then solve for x. Since I am finding the value of y, I'm going to solve for x so that the y value stays in my equation. Is equal to 5x. So x is equal to 100 minus 6y over 5. Or, yeah, that's fine. Okay, so let's go ahead and plug that into our primary equation. So I get area is equal to 4, I'm going to put the y first, times 100 minus 6y, all over 5. Okay, and this reduces to 80y minus 24 over 5y squared. All right, so next up, I will take the first derivative, so dA dy, and I get 80 minus 48 over 5y. And then we need our critical numbers. So when the derivative is equal to 0, so 80 minus 48 over 5y. So 48 over 5y is equal to 80, reciprocal. So 5 over 48, and I get y is equal to 25 over 3, which is about, oh, actually, it's exactly equal to 8.3 bar. All right, so we are now going to test to make sure that we are actually maximizing the fence when I plug in this critical number. So on the end, the fencing has to be, the area has to be greater than 0. So I'm going to use an open circle. And then 25 over 3, which is just past 8. So I'll just test f prime of 10. It's f prime of 1 and f prime of 10. And I get that f prime of 1 is a positive value, and f prime of 10 is a negative value. What I did was I used a graph to figure out my positives and negatives, and I just substituted in my derivative, so 80 minus 48 over 5x. So you can put this in for y1 in your calculator. And then I see graphically that the outputs are positive on values that are less than 8.3 bar, and they are negative on values that are greater than 8.3 bar. So the graph is increasing and then decreasing. So we at 25 over 3, y equals 25 over 3, we will have a relative max. So we maximize the fenced area when y is equal to 25 over 3 yards. Okay, last one for, oh, sorry. So there it is. We have our positive and our negative, and then that gives us our relative max. So we have a maximum fenced area when y is equal to 25 over 3 yards. Okay,